So here's what we have so far. This was the big idea from last time. And we were able to define 6 trig functions as measures of the angle formed in the xy plane from the positive x-axis to an arbitrary point in the plane. I've been drawing the point in the first quadrant, but it doesn't have to be. But if I put this point with ordered pairs x and y here and draw the ray from the origin through that point, the angle theta that I'm talking about is right here. From that, we can drop the perpendicular segment down and form a right triangle where this length is the same as the x coordinate. That height is the same as the y coordinate. And this number is the hypotenuse of a right triangle. Let's just call it r for now, where x squared plus y squared is equal to r squared. And then we had our 6 trig functions as functions of this angle here. We have the sine of angle theta is the y value divided by r. The cosine of angle theta is this x value divided by r. And the tangent of angle theta is the slope of that. It's y over x. Then we had the reciprocals of these. Reciprocals. We call them the reciprocal identities. The reciprocal of the sine is called the cosecant of that angle. And it's r divided by y. The reciprocal of the cosine was the secant. It's 1 over the cosine. So that's r divided by x. 1 over the tangent was called the cotangent. And so that's x divided by y. And then I showed you how we can substitute in, say, take this line and divide everything by r squared. And then this becomes x squared over r squared plus y squared over r squared is r squared over r squared. But x over r was cosine, so x over r squared was cosine squared. So we had that the cosine squared of theta plus this became y squared over r squared, and that was the sine of theta squared. And this was r squared over r squared, so that was equal to 1. If we further manipulated this, for instance, if I divide everything by x squared over x squared is 1. Y squared over x squared will be tangent squared. R squared divided by x squared will be secant squared. So another version of this identity was 1 plus the tangent squared of angle theta was equal to the secant squared. Or if I wrote it this way, divide everything by y squared. X squared over y squared will give you a cotangent squared right there. Y squared over y squared gives you a 1 right there. And r squared over y squared will give you cosecant squared there. So we call these the Pythagorean identities because they all come from that. Then we also said that we can determine the sign, SIGN, of our trig functions based upon what quadrant things were in. R is always positive. There's no R there. So sine is positive wherever y is positive, and that's in quadrants 1 and 2. It's negative in the other 2 quadrants. Cosine is positive wherever x is positive. So that was in 1 and 4. Tangent is positive where both x and y have the same sign, and that's in 1 and 3. And the reciprocals follow those. And so our memory device was this, that all of the trig functions were positive in here, And then the sine and 1 over the sine was positive there. So I said you can remember that by students. The tangent and 1 over the tangent's positive here. So I said we remember that with take. And cosine and 1 over the cosine. Positive here. All positive, sine and 1 over sine, positive here. Tangent 1 over tangent, positive here. Calculus 1 over calculus. Cosine and 1 over cosine, positive here. Does that sound like something we did? And then I left you for the weekend telling you that if you knew the value of the trig function at one angle, and you know the quadrant that the angle's in, you know all 6 of them. So I wanted to do an example of that right now. Okay, so my example will be, suppose the cosine of an angle, maybe I should use the same example I did this morning since that's on those notes, is, I hate these numbers, so I'm going to change them, 5 square root of 6 over 6, and angle theta is in quadrant 4. Find the values of the other 5 trig functions. Or I can go across on here. Guys at home, can you see and hear me? Actually see the board, I don't care if you see me. Good, good. You can ask questions through the chat feature or through the microphone if you have any questions. And I hope I can hear you. But I definitely can see the chat. I've got the wrong notes, so it's not concern for me. Okay. Several ways you can do this. Probably the easiest way is to draw you a triangle with the angle theta formed with the x-axis and some point in quadrant 4, where x has a length of 5 square root of 6. And the hypotenuse has a length of 6. And then we can figure out the adjacent or the other side. That might be the quickest way to do this. So we just draw an angle in quadrant 4. So we always make the x-axis one of the sides of the triangle, no matter where we draw it. We're drawing it in quadrant 1, we draw it up like that. In quadrant 2, we draw it up like that. In quadrant 3, we have it coming, always vertex angle at the origin. So we're going to go over 5 times the square root of 6. That's the, remember, that's x over r. So we're going to go over 5 square root of 6, down a certain length, and then r is this length. And the angle theta is here. Okay, so I knew that was x because I have a cosine. Now we need to find the y value, and you can do that with the Pythagorean theorem. This length squared, here's the right angle. Again, the right angle is always formed with the x-axis. This angle squared plus that angle squared is the hypotenuse squared. So let me see if you guys can all find the length of the hypotenuse. I'll try triangles over here while we were thinking. That's what the second quadrant would look like. Third quadrant would be down here. Fourth quadrant is like that. These one of these four triangles. Maybe what you're doing on your paper right now is you're finding the length of y with this equation here. Leg squared plus leg squared is hypotenuse squared. Always put the longest length for the hypotenuse there. Let's do that up. Not that for a zoom, just pull the camera. I'm so old school. Okay, to do this multiplication, you take 5 times 5, square root of 6 times square root of 6, and then multiply them together. So 5 times 5 is 25, the square root of 6 times the square root of 6 is 6. So this is 25 times 6. And that's going to be, I think I've got my longest side. That's not in the right proportion, is it? This is too long. Yeah, that's too long. I don't want a negative number. So I said this wrong. How about, I gotta change that. Why didn't you tell me? X can't be longer than R. Why don't I just flip them upside down? Flip it over with my, I'll even use towel. So let's say this the other way. That's what I get for making up numbers. Okay. And now let's do it the other way. The longest side has to be the hypotenuse. Just has to be. That's the world that we live in. Oh, that 6 is bad. Okay, so this time we have 6 squared plus y squared is 5 square root of 6 squared. So I have 36 plus y squared, and this was 25 times 6. Let's see, 4 times 25 is 100, so 6 times 25 would be 150. So this is 150 over here. I'm going to solve for y squared, so my next step, I'm going to subtract 36 from 150. 114, so y is the square root of 114, but look at the y in quadrant 4. It's negative because it's going down, right? So here we're going to put the minus sign on it. Okay. Now from that picture, we can get all the other trig functions. For instance, the sine of that angle theta is that y value divided by r. And so it's the square root of 114 negative divided by 5 square root of 6. The tangent of that angle theta is the y divided by the x. The y is negative square root of 114. The x is a positive 6. Now we start flipping them over. The reciprocal of the cosine is the secant. So the secant is 5 squared of 6 over 6, and it is positive. The reciprocal of the sine is the cosecant. So that's going to be 5 square root of 6 over negative square root of 114. I'll just put the negative on top. And then finally, the reciprocal of the tangent is the cotangent. And so that's going to be 6 over the negative square root of 114. And again, I'll just put the negative on the top. Yes?
On a quiz or a test, you have to rationalize that sign.
Yeah, you don't have to rationalize for me. Are you having any trouble doing it for web work? You didn't have to do any of the web work where you had to rationalize? You had to, did you do okay? Yeah, numbers are not important. I want to see if you understand the concept. So you don't have to rationalize for me, unless you want to. It's America. Did that make you think of anything you wanted to ask? That was the last bit there of section 1.4. Okay. Now in chapter 1, we defined these angles as making an angle with either the positive or the negative x-axis and one of the vertices of the triangle that we draw at the origin. But in chapter 2, we can generalize that. I can take a triangle and just put it out in space. Don't have to put it on a grid. And I can figure out the lengths of the sides and define all of our trig functions in terms of the lengths of the sides. For instance, if I just rub this off and don't put it on a grid and have some numbers here, the side opposite the right angle is always called the hypotenuse. If I label this as angle theta, then there's going to be a side of the triangle that forms that angle with the hypotenuse. That's going to be called the adjacent side. It's adjacent to the angle. And there's going to be a side that's opposite the angle, and that'll be called the opposite side. Isn't that clever nomenclature? Adjacent, opposite, hypotenuse. And now I'm going to write all of these in terms of sides of the triangle with those names. So that's what we do in chapter 2 in section 2.1. We're going to talk about acute right triangles. What does acute mean? The angles inside this triangle that are not right angles both have measures smaller than 90 degrees. So if all of the angles have measures smaller than 90 degrees, our trig functions, all of them, are going to be positive numbers, right? Because angles measure smaller than 90 degrees correspond to first degree, first quadrant angles. So here's an example of an acute right triangle. I'm going to draw it this way just for the heck of it. This angle and that angle are both smaller than 90 degrees. So suppose I put my angle theta here, and this side is called the adjacent side. This side is called the opposite side. And this, of course, opposite the right angle is the hypotenuse. I can also draw my triangle this way. If I want, I can put my angle up here. If I call that my angle, then this side is adjacent to it. this side is opposite, and this side's the hypotenuse. But now think about how that would correspond to our coordinate trigonometry. We would have to take, say, these things and rotate them so that the origin corresponds to here. If you think of it in terms of that way, if the origin corresponds to here by, say, rotating that however many degrees, then this would always correspond to X, and this would always correspond to Y. But if we look at this or that, then we can define the sine of angle theta as the Y over R. In this picture, it's opposite over hypotenuse. Right, if it's this angle, and I tilt this so that this is at the origin, I'd have to rotate that 90 degrees, and then that's at the origin, and this would be a Y value, and that would still be an R. Okay. Cosine of angle theta is defined as the length of the adjacent side over the hypotenuse. And then the tangent of angle theta would be the opposite side over the adjacent side. Then flip these over and you have our reciprocal identities. We'll have the cosecant of angle theta is the hypotenuse over the opposite. The secant of angle theta is the hypotenuse over the adjacent. And the cotangent of angle theta is the adjacent over the opposite. So if you've had trig before, maybe you've seen this little memory device. So Katoa, that the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. You know what a Pythagorean triple is? The Pythagorean identity says that in a right triangle, the sum of the squares of the legs is equal to the hypotenuse. Well, there are some whole numbers that satisfy x squared plus y squared is r squared. An example of a Pythagorean triple that are whole number values there are a 3, 4, 5 triangle. Sorry, didn't need to do that. Why are you ringing? Stop. Um, 3 squared plus 4 squared is 9 plus 16, which is 25. 25 is 5 squared. So 3, 4, 5 is an example of a Pythagorean triple. Another Pythagorean triple is, I don't know, you got another,
12 and 13.
say again, 5, 12, and 13?
Yes.
5 squared plus 12 squared is 13 squared. Any others? There's a whole bunch more. Those are the only two I remember. So let's draw a 5, 12, 13 triangle, and let's find the values of the trig functions for that particular arrangement. All right, so let's see, let's go this way. All right, so let's see. You do know that in any triangle, the smaller angle is opposite the smaller side. Right, the largest side is opposite the 90-degree angle, and that leaves these two left over. So let's put this side is 5, this one is 12, and that one is 13. So these were examples of a Pythagorean triple. There's 3, 4, 5, 5, 12, 13. And then multiples of these. For instance, if I had a 15, 20, 25, every multiple of these just generates similar triangles. Okay, so what I want you to do, let's put angle theta right here. And I want you to find all our trig values: sine theta, cosine theta, tan theta, cosecant theta, secant theta, and cotangent of theta. Got them? All right, so here we go. Sine was opposite over hypotenuse. So if I labeled this as theta, opposite is 5, hypotenuse is 13. So that makes cosine 12 over 13. And the tangent is opposite over adjacent, so that'll be 5 over 12. So I've gotten to where I write these. The reciprocals are here. So let's just flip these over. Cosecant is 13 over 5. Secant is 13 over 12. Tangent is 12 over 5. Get them all? Good, 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 good. This is the easy part of trig. I hope you find it easy. Not entirely thrilling. Can't thrill you every day. I can barely thrill you 2 times a week. There's a reason this is called a cosine. And this one's called a cotangent. And that one's a cosecant. They're co-functions of one another. 2 functions are said to be co-functions if they take on the same values, but a fixed distance away from each other. Let me draw you this triangle again, and this time just label the vertices. I'll draw it this way. So let's call this vertex A, this one up here vertex B, and put the right angle at vertex C. And let's call the side opposite angle or opposite vertex A, let's call it little a. Put a little b as the side opposite angle B and a lowercase c opposite vertex C. So to make vertex C look more capitalized, I'll put these little thingies on the capital C. So if I say this, the sine of the angle at vertex A, in terms of the lowercase letters A, B, and C, what would it be? A over C. What do you know about the measures of angle A and angle B? They're both less than 90 because this is 90. What's the sum of the angles in the triangle? 180. Here's 90 of that 180. That leaves 90 degrees left to be shared by A and B. When 2 angles measures add to 90 degrees, they're called complementary. These are complementary angles. Angle A and angle B are complementary. What is the cosine of angle B? Cosine of this angle up here. It's A over C, the same A over C. They're co-functions in that they take on the same value at complementary angles. Let's look at the other two trig functions. The reciprocal of the sine was the cosecant. So the cosecant of angle A is C over A. That's going to be the same as the reciprocal of the cosine, which is the secant of angle B. Flip that over and you get C over A again. Cosecant and secant, co-functions. They take on the exact same ratio at complementary angles. Tangent and cotangent are going to do that. Let's look at the tangent, say, of angle A. In terms of the letters that I have labeled there, what's the tangent of angle A? Opposite over. That should be the same thing as the cotangent of that complementary angle. The cotangent is adjacent over opposite. So the cotangent of this angle will be A over B. So what I'm going to write now is this in general as something called cofunction identities. So this observation gives us these cofunction identities. That the sine of any angle and the cosine of the complement of that angle are always equal. Sine of any angle and the cosine of the complement of that angle are always equal. So for instance, the sine of 2 degrees is equal to the cosine of? Sine of 2 degrees is the same as the cosine of 88 degrees. Always. Okay? For our acute angles. Same deal with the tangent. The tangent and the cotangent take on the same values, but on 90-degree angles away from each other. And the secant and the cosecant oops, got me a 90 here. Those are our cofunction identities. So that gives us the secret to solving some trig equations. For example, find value of theta that makes the following equation true. Here's your equation. The cotangent of theta minus 8 degrees is equal to the tangent of 4 theta plus 13 degrees. So this is what I'm telling you here. The tangent of one quantity is equal to the cotangent of another quantity only if the two things in the parentheses add up to 90 degrees. For a tangent to equal a cotangent, their two angles must be complementary. So that's what we start by saying. Cotangent is equal to a tangent only if these angles must be complementary. That angle plus that angle has to add to 90 degrees. And now we have an algebra problem. Theta minus 8 plus 4 theta plus 13 has to be 90 degrees. Now just get lazy and leave out the degree symbol. And now solve for theta. Put this one together with that one and get 5 theta. Put the minus 8 together with the 13 and get plus 5. So this says 5 theta plus 5 is equal to 90. Yes.
So in terms of adding thetas together, it's not like a variable.
It is like a variable. 1 theta plus 4 theta gave me 5 of them.
Okay. I don't know where my head's at.
It's 3 o'clock in the afternoon. Your head is where your body wants to be, napping. Right? In this prime nap time for people your age? And don't laugh at me when I'm asleep at 10 o'clock at night. 'Cause I don't nap at 3 o'clock in the afternoon. It's go time for me. Go, real go, but go. Okay, a 5 theta plus 5 is 90. Subtract 5 from both sides, and we have 5 theta is 85. Divide 85 by 5, and I bet you get 17. Right? So this would say the cotangent of, what, 9 degrees? Oh, shoot, I don't want to multiply that by 4. Well, 9 degrees is complementary with 81 degrees. So I bet that adds to 81 when theta is 17. Right? Good deal. Good deal. So sines are equal to cosines if their angles are complementary. Secants are equal to cosecants if their angles are complementary. Tangents are equal to cotangents if their angles are complementary. That's the nature of the co-business. They weren't named that just because they ran out of names. Next. Next. Okay, now I want to see how these functions themselves grow or don't or shrink as theta grows. So I'm going to take a fixed line segment length. Let me see if I've got something I can use as a fixed length. Yes, this is going to be my length of R. And I'm going to make a small angle, a larger angle, and a larger angle, and construct the triangles with that hypotenuse. And as theta grows, what happens to the sine of theta and the cosine of theta and the tangent of theta? Let's rip this part off. Okay, so as the angle grows, what happens to sine of theta, cosine of theta, and the tangent of theta. So let me put a horizontal line here. Let's make, here's my, try to keep your hypotenuse the same length. So let's make a relatively small angle with that horizontal line. Oops. There's angle theta here. Let me go over to here, make a bigger angle. There's angle theta that's a little bit larger. Now we'll go over to here and make angle theta almost a 90-degree angle. And from those, I want to construct my right triangles. So I drop the perpendicular down from that end point of R. So we're keeping R fixed. And we're going to look at how these grow because we can see how X and Y grow. All of these have the same length. But notice from here to here to here, X is getting smaller. Agree? What about the Y values? Good golly, they're getting bigger. Y1 is smaller than Y2, which is in turn smaller than Y3. So as theta grows for fixed R, Y grows. That means the sine of theta will increase in size as theta grows. Agreed? Sine is Y over R. So the sine here is a smaller number than the sine here is a smaller number than the sine here. So the sine, Y1 over R is going to be smaller than Y2 over R. It's going to be smaller than Y3 over R. R, come on. So I'm going to call these subscripted thetas because they're changing. So as theta grows, then sine theta grows. Sine of 2 degrees is smaller than the sine of 32 degrees is smaller than the sine of 62 degrees. It's opposite for cosine. Cosine is X over R. The cosine of this angle is going to be a bigger number than the cosine of this angle, and still bigger than the cosine of this angle. So the cosine of theta will decrease because X1 over R is going to be bigger than X2 over R is going to be bigger than X3 over R. So as theta grows, the cosine of theta decreases. The cosine of 2 degrees is going to be bigger than the cosine of 32 degrees. Now let's look at the tangent of these angles. The tangent is going to be Y over X So let's look at the ratios of y1 to x1, compare it to y2 to x2, and y3 to x3. In these three fractions, this is the smallest denominator, and that has the biggest denominator. The smallest denominator corresponds to the bigger numerator. So take a fraction where the numerator is getting bigger and the denominator is getting smaller. What happens to the size of the overall fraction? It's getting bigger, right? So this one falls that way. So the tangent does what the sine does. Tangent of 2 degrees is going to be smaller than the tangent of 32 degrees. Okay? I always need a picture to remind me of that. Does that make sense to you? So let me check if it makes sense to you. Fill in the blank with a less than symbol or a greater than symbol. Just in case you've forgotten. The symbol opens up to the bigger number. So let's put cosine of 55 degrees compared to the cosine of 40 degrees. Tangent of 18 degrees compared to the tangent of 81 degrees. And the sine of 49 degrees and the sine of 9 degrees. Well, we can add one more. We can answer that question. Go ahead and think about it. Draw it in there lightly unless you're real confident, and whip out the ink pen and put your symbol in there. We'll go over. Give it a shot. Try your logical reasoning on this and see if you know greater than or less than. I'll just stand here and stare at you. Who's that? Okay. Just wondering if, oh my God, how much longer does class last? Oh my gosh. Could it possibly last another? "30 minutes, that's nothing. We'll put money on it, make it more fun, make it more challenging. For each one you miss, you give me $1. You can Venmo me. That cheap stuff, mind you. I want a medium good bottle of wine. So in our comparison, let's see, 50, this is 90 degrees, right? That's 0 degrees. Halfway there is about 45 degrees. So 55 degrees is here. Cosine is y over r. And 40 degrees is about here, y over r. Which one has the larger y? 55 degrees or the 40 degrees? I'm sorry, cosine is x over r, so that wrong. Which one has the bigger x? The 55-degree one if I drop the perpendicular down, or the 40-degree one? That one has the bigger x. So the bigger side is here. Okay. So now we're looking at the ratio to y over x. So 18 degrees is pretty flat, small y, big X. 81 degrees, big Y, small x. So big Y, small x makes a bigger ratio than smaller y, bigger x. So that means which one was bigger? Good. Sine again is y over r. R is the length of my arm. Y is dropped to the horizontal. So 49 degrees is here. The y value, 9 degrees is here. Which one's bigger?
49.
Sine of 49. Okay. Now let's see a 10-degree angle. 10 degree, that's 90, so about 1/9 of the way here. Which is going to be the bigger number? Which is the bigger number? X over r is going to be bigger, so which trig function is bigger? Cosine is x over r. It was kind of fun, wasn't it? Did I get any dollars? Drinking water? Drinking water tonight? It's not going to help me grade any papers. Okay, now we're going to look at some of our special triangles. Not the 3, 4, 5 or the 5, 12, 13. We're going to look at equilateral triangles and isosceles triangles. Those triangles are named based upon the lengths of their sides. In an equilateral triangle, all 3 sides are congruent. But also in an equilateral triangle, all 3 angles are congruent. What are the measures of the angles in an equilateral triangle? 60 degrees. You draw us an equilateral triangle up here. Make all 3 lengths the same. These are all going to be 60 degrees. Now let's over here draw an isosceles triangle. Isosceles has 2 sides that are congruent. I want to make an isosceles right triangle. Let's see, let's put a leg. Same length here. And then the hypotenuse. I want the legs to be the same length. Come on, hypotenuse, work with me. There. So that's the same length as that. Here, all these are the same length. Those are our 2 special triangles. In an equilateral triangle, the altitude drawn from a vertex angle to the opposite side does 2 things. It bisects the angle from which you draw the altitude, and it bisects the opposite side. The altitude makes a right angle as well. That's the definition of an altitude. So in an isosceles right triangle, I can cut this equilateral triangle up into a triangle that has a 60-degree angle, a 90-degree angle, and now I just bisected this angle, so it's a 30-degree angle. Angles opposite congruent sides are themselves congruent. Here's 90 degrees of the 180 degrees. That leaves these two angles to add to 90 degrees, and they're congruent. So what's the measure of each of the angles in an isosceles right triangle? 45 degrees. Now, if I draw another isosceles right triangle, it will be similar to this one. In other words, the sides will be proportional. The ratio, say, of this to another isosceles right triangle will be the same. Same deal if I were to reproduce a 30, 60, 90 triangle. The sides will be of proportion. So to make numbers nice, let's say that this equilateral triangle had sides that were each 2 units long. So if this was 2 units, then this length from here to here is now 1. And I just want you to look at the right triangle formed over here. So I want to know next, use your Pythagorean theorem to find the length of h in that triangle. One leg is 1, one leg is h, the hypotenuse is 2. Find the length of h. That h squared plus 1 squared is equal to 2 squared. So I have 4. I'm going to take this one away from there. So I got 4 minus 1 is 3. So do you agree that h has a length of the square root of 3?
Yes.
Okay, let's suppose both of these have length of 1. I want you to find the length of the hypotenuse over here. Got it already? C squared is 1 squared plus 1 squared. So c squared is 2, c is the square root of 2. From these two pictures, we can get the sine, cosine, and tangent of 30 degrees, the sine, cosine, and tangent of 60 degrees, the sine, cosine, and tangent of 45 degrees. And on Thursday of last week, we got the values of all of our trig functions at 0 degrees, 90 degrees, 180 degrees, 270, and 360. So I'm going to put them all in a table. I'm just going to use the first quadrant angles. Those are going to be called our reference angles. They're acute angles that we're going to know the exact values of our trig functions of without having to go to a calculator. So let's make a table using those pictures. So the angles that I'm interested in, these are all going to be acute, so I'm going to call them reference angles. Could have moved over more, but I didn't. I'm going to start with 0 degrees. Then we'll go, the next size will be 30 degrees. The next size will be 45. Then 60. And then finally 90. I've always done my table this way. I'm going to put the sine of the angle right here. Then the cosine of the angle right here. And then the tangent of the angle right here. And we're going to have a total of 4 columns. Okay, let's go across the 0 degrees. A 0-degree angle is technically a ray on the x-axis. So it has a positive x coordinate. The y coordinate is 0, and r is the same as the x coordinate. So if r and x are the same, then the ratio x over r is going to simplify to 1. Which one of these has a ratio of x over r? Cosine. So this is going to be 1. But the sine is y over r. The y value is going to be 0 because that angle was coterminal with the x-axis. What about the tangent? The tangent is y over x. 0. The y value is 0. All right, now let's look at this angle up here and use our opposite adjacent hypotenuse description based on this angle. Sine is, let me write it up here, opposite over hypotenuse. So using that red 30-degree angle, what is the ratio of the opposite over the hypotenuse? 1/2. What is the cosine of that angle? What is the adjacent over the hypotenuse? Square root of 3 divided by 2. Tangent was opposite over adjacent.
So
1 over root 3. Now, we almost always rationalize when we learn these values. If I multiply top and bottom of that by the square root of 3, here's the number that I'd really like you to remember. Square root of 3 over 3. Now we're over there in the isosceles right triangle, using either of those 45-degree angles. What's the sine of 45 degrees? Opposite over hypotenuse.
1 over the square root.
1 over the square root of 2. What does that look like if you rationalize its denominator? It's a square root of 2 up here and gives you a 2 down there if you multiply top and bottom by square root of 2. Do you agree that the cosine is the same?
Yes.
What about the tangent? What's the opposite over the adjacent going to give you? 1. Now notice that 60 degrees and 30 degrees are complementary. So that means that the sine of 60 degrees has to be the same number as the cosine of 30 degrees. The cosine of 30 degrees was square root of 3 over 2. Let's look. The sine of 60 degrees is opposite over hypotenuse. It's amazing. The cosine of 60 degrees has to be the same as the sine of 30 degrees. So it should give me a 1/2. Cosine is adjacent over hypotenuse. So that does agree with our picture. Tangent. Tangent of 60 degrees is opposite over adjacent. So the square root of 3 divided by 1, and I'm just going to write that as the square root of 3. Now let's go look at a 90-degree angle. At a 90-degree angle, x is 0, y is whatever number r is. So y and r are the same. That means y divided by r is going to give me 1. So which one of our trig functions is y over r? Sine. So it's going to be 1 here. Cosine is x over r, but on a vertical line, the x is 0. And tangent is y divided by x. Y divided by x, we're going to have 1 over 0. So that's not going to be defined. So one thing I want you to notice is that this number over here in the tangent column is the same as taking the value of the sine and dividing it by the cosine. Take 1/2 and divide it by the square root of 3 over 2. We divide one fraction by another by flipping and multiplying. The 2's will cancel, leaving us with 1 over the square root of 3, which we rationalize to that. So another way to remember the tangent is when I build the table in this way, that's why I always put sine first. that the tangent of any angle theta is the same as the sine of that angle divided by the cosine of that angle. And that's why I build that table that way. You can build that table by using these pictures. That table we need to have in our head from here on out. Like when you're on your 132 years old, I want you still to be able to know these values. You're on your deathbed. And by the time you guys reach, whenever you guys get old, 132 will be about the time people start dying. So I want you to memorize those. So let me show you a quick way to memorize them. Using the picture, you can do it with logical reasoning. Or you can just dumb, blind luck build it. You do have to remember the first column. 0, 30, 45, 60, 90. I always put the sine first, cosine second. And then I count from 0 to 4. Down on the sine, up on the cosine. The next thing I do is I take the square roots of those numbers. Then I divide those numbers by 2. And the last thing I do is simplify. The square root of 0 is 0. 0 divided by 2 is 0. So that one and that one simplify to 0. Square root of 4 is 2. 2 divided by 2 gives me 1. So that one and that one give me 1. Square root of 1 is just 1. So each of these is a half. And now I have that table. If I want tangent, I just divide left column by right column. Okay? So that's in the nature of the SOHCAHTOA, a quick way to remember this stuff. So suppose I wanted to know, without the pictures, just with the table of values. Secant of 45 degrees. That's my thought process. Yes, sir.
Just take the reciprocal of the cosine.
That's all there is to it. Go over there, grab the cosine of 45 degrees and flip it over. That's what it means to take the reciprocal. But if I rationalize this, it simplifies pretty nicely. Let's multiply top and bottom by the square root of 2. So the numerator is 2 square root of 2. Multiply the 2 square roots of 2 together on the bottom, and you just get 2. So those 2's cancel. So the secant of 45 degrees is the square root of 2. Now the cotangent of 60 degrees. Cotangent of 60 degrees. Which one am I flipping over? Cotangent is the reciprocal of the tangent. So I'm going to flip over the tangent value of 60 degrees. What does that look like if you rationalize the denominator? So I'm doing that, but I'm multiplying top and bottom by the square root of 3. So I guess one more. I've got a cosecant of 30 degrees. Who's got it? Who? Went over the sine of 30 degrees. Sine of 30 degrees is a half. Over a half is 2. Okay. So we're going to spit those out and spit them out and spit them out. But what we're going to do next time is we're going to take angles that are not acute. 135 degrees. 120 degrees. 240 degrees. And we're going to relate those back to the angles that are here, based upon where they are if we form them with a circle, a unit circle. So when we have obtuse angles, they're going to have values of the trig functions that are somewhat equivalent to the values of the trig functions here, except for then we've got to consider what quadrant the obtuse angle is in. Doesn't that sound like fun? And I'd love to do it now since we had some extra time, but my morning class didn't have this extra time. And this is where I ended on my morning class. Would you object to ending class, what, 8 minutes early? Anybody? Anybody object? You guys. Questions for you guys at all? Just out here.